Good morning. I'm Anuj Sharma. I'm an associate professor at Iowa State University, and today I'll be talking about application of distribution learning in transportation engineering. I'll be accompanied with my colleague Arya, and he will be talking on how going in depth in a lot of case studies, how we have implemented these things. So I'll just give a brief outline on the work which is being done in our lab. This work has been supported by multiple members of our team, and we are fortunate enough to present in this workshop. So to just give a outline on why is our work important, obviously there are delays associated with poor traffic management, and also there are cases where the safety can be impacted. So this just gives you a overview of why uh, using some of the deep models can really change operations in traffic management. So typically this is a scene in Iowa where in traffic management center, a person keeps on browsing different cameras, taking a look at if there's something is going bad on the road. And if they don't see anything, they move across and look at other cameras. In this scenario, as soon as the person moved across, there was a crash at this point. It took almost 5 minutes for the operator to come back to this crash, and another 6 minutes to inform people, which means that the time from the incident happening and for people finding out that there was a crash on the road was almost 11 minutes, and which is very critical, both in terms of congestion mitigation, in terms of probability of increasing rear end collisions because of secondary crashes and things like that. If there was a way that we could automatically process multiple streams of data coming from cameras and detect all these incidents, that would significantly improve the traffic incident management in transportation. So the role of distributed processing of large volumes of data is very important, both for inferencing as well as training better models. Our group has been working on some of these situations. So in this case, when we started the work, we were kind of training simple models which can detect counts on a given section of the road. The counts are important so that you can understand how many vehicles or trucks are crossing a specific intersection, and can help with signal improvements and other such things. So these were simpler models, but then we start looking into classification of elements, because now we might want to prioritize a specific mode of transportation over the other. Again, for coming up with better and better models, you need even more detection. But one other challenge which is faced by typical transportation industry is that the camera keeps on moving. So you might be looking in one direction, then the person might move it to the other directions. And that is one of the challenge, that whatever technique we come up with should work on different angles and different zoom levels. Then there is kind of how can we understand where the camera is pointing, and can we detect that thing and do even more stuff. The other challenge which is faced by our industry is in terms of detecting different kind of objects. So it can be not just freeway traffic, it can be traffic during a signalized intersection, and then in that case pedestrians become important. We are trying to track their safety, and this is an interesting example which I wanted to show here. Let me pause this video and focus on this video a little bit more. So you see over here that we have trained the model with the pedestrian, and we have trained the model with the cyclist, but this is a scenario which comes into play where a person walks in with another person with wheelchair, and then the model keeps on getting confused whether it's a pedestrian or something else. So always all the time these cases happen where we might get another class, and we have to keep on training these models. So this is another challenge which is often seen in transportation. The other challenge we try to solve in our area, so we talked about just simple detection, counting in a zone, region of interest. We talked about getting the trajectory information. The other challenge would be converting the data which is measured in pixels into something which is associated with geometry. So can I find out, can I portray it back and overlay it in on actual physical map, and which is important problem, because we are not only interested in pixel location of a vehicle, we are also interested in geospatial location of that vehicle, so that other objective functions can be derived. We can find out whether there is, what is the speed at which they are traveling. We can find out how close they were, if they were having any kind of traffic conflicts and things like that. So as each of these models become better and better, we need more and more powerful resources so that we can do all this analytics on in real time, and that on a large number of cameras, and that is some of the things that can be solved with parallel processing and distributed computing. And the other problems we like, as I said, there are other problems where we are looking at very heavy models, like models which require some kind of uh, like optical flow based analysis, because we want to remove some of the areas which are moving from image to image, but we still want to detect there is a vehicle stuck on the side of the road, even though there is a lot of vehicles which are present on the street, and even these processes are very heavy. So it becomes that at some point it becomes imperative, if you want to design a real world application, you have to go towards distributed computing, and that's where RocketML and other such providers become important. Again, another issue we see is different conditions. So it might be that what more and more data needed to train under varying weather conditions. So even though on a theoretical level it might seem simple, if you want to actually run an application that can be implemented in real world scenario, that becomes a tough, and you might end up deploying heavier and heavier models. The other application which is important in transportation is understanding driver behavior. So in this case, we are using outward facing camera, where we are trying to detect what are these people, like what are the objects outside. We might be interested in identifying facial features where the person is looking, and also we might be interested in finding out whether a person, how the vehicle is moving. So there is this whole petabytes of data which were collected by NDS studies, naturalistic driving studies. This data is sitting there but has to be processed, and so far it was being processed by manual annotators, and there is a limitation on how much data can be reduced using this manual annotators. So now we are moving towards, can we use deep models to actually come up with uh, incidents of interest, and also tie them together to do some behavioral modeling. Again, the challenges, there are a lot of challenges. There are challenges with compression, that because this data was collected several years back, it was not possible to record really high quality images. So they were compressed. The problem with compression is that when during the daytime conditions, the feature maps looks very reasonable, but if you mix nighttime condition with compression, the feature maps really distorts, and it is difficult for machines to identify what is going on. So that these are the challenges we are facing. One of the ways we can address this, we thought, would be using some kind of a process where you can train some cyclegans to convert the daytime images to nighttime, and vice versa. But again, there are a lot of challenges even doing that in producing higher quality images, or changing the conditions of images, because there are some artifacts which are added, and these just show when the figure on the left, which was taken, figure on the top is taken during the daytime, and if you used a cycle GAN to convert it into the nighttime image, there were a lot of arbitrary noise that was added to the scene, just because the data on which it was trained kind of uh, predisposed to be like that. So in our case, we are using Rocket ML for not only distributed computing, but also data science workback management. I will now give opportunity to Arya to take over the conversation and give some an in-depth example of how we are using distributed inferencing as well as distributed.
Hello everyone, my name is Arya Hairat, and in the rest of this session, I will present some application of distribution computing in the field of transportation. Let's start talking about first case study. As we discussed, advanced driver assistance systems known as ADAS are trying to help driver to drive safely by interpreting the driving circumstances by using input data from sensors like camera or radar. In this case, we focused on visual data from front cameras. Usually the main objects which drivers should take care of them while driving are other vehicles, pedestrian, traffic signals, and traffic signs. Respectively, in this project, we also focused on detecting these three objects. Important constraint on this project is to detect everything in a real-time manner and report it to the next model. Otherwise, the model cannot save the driver from any incident. Our solution for this project was using YOLO v5, which is pre-trained on Coco dataset, which has 80 different classes. However, in this project, in order to make the model faster and more accurate, we retrain it on our dataset. Before talking about scaling up the solution, let's summarize performance of the model on a single GPU. For this experiment, we have used a T4 GPU on the AWS. In this experiment, a video with a length of 1 minute, including 1500 frames, is analyzed. Inferencing a model usually has 4 different components. At first, we upload the model, then read the images, make the inference on the images, and write the results out. In this plot, we have tried to show how much each component is time consuming. As you can see in this figure, reading the image and inferencing model both took a little bit more than half of the whole process. And it revealed the importance of model structure in the inference time. If for each video we want to load the model separately, we should spend at least 5 seconds per each video. Also, in this experiment, we only were routing the results after each 25 frames of inference altogether. Nevertheless, this portion takes more than 6 seconds. In the model, if we can save the results in a data frame or any other data structure up to end of the video and write all those data once, it could save us a lot of time. It all depends on your application and how you need to save your results. Okay, let's talk about the design of experiments in this project. In order to investigate the impact of cluster computing on the inference, we designed 4 different types of cluster with different components, including P3, G4DN, C5, and T2. In each cluster, we also run the model on different number of instances from 2 child nodes to 5 child nodes. You can see detailed properties of these different instances here on this table. The first 2 instances have equipped with GPU, and the last 2 ones do not have any GPU. Also, please note that we sorted these instances here by their price. So the P3 has the most expensive cost, and T2 is the cheapest one. Finally, to create these clusters, we have used RocketML inference interface to easily scale up the cluster and make the inference on them. Okay, let's talk about implementation of the model. For this implementation, we have used MPI4Py library to distribute the job on a cluster. So first, we created our convol based on type and number of instances on the cluster. Also, since our data is stored on S3 bucket, we will give their links to the model. Here in this step, we check if the number of videos are more than number of nodes and get number of videos which we should process on each node. In the next step, on each node, we will load our model first, so we do not need to load model for each video separately. Then we start distributing videos between nodes. For each video, we need to download the video from S3 bucket into master node, and then give access of those videos to the particular child node and make the inference on that video. Finally, the result will be written back on the master node, and the video will be deleted to saving space. Okay, let's see how the model performs these different clusters. Before talking about a result, please keep in mind that the batch size in this project was equal to 1, which means at each time there was only one video we're analyzing on each node. Also, in that these tests, we make the inference on 20 videos, all with the same properties that we have talked before. As you can see, for each type of cluster, we change the number of nodes from 2 to 5. And as it can be observed here, we can almost say by increasing number of nodes, inference time will reduce linearly. On the other hand, as I mentioned before, G4DN instance was cheaper than P3 instance by magnitude of about 6. However, as you can see here, in this figure, G4DN cluster outperforms the P3 cluster. The main reason for this fact is that Tesla V100 GPU, which is the GPU in P3 instance, is highly optimized for training, and it is not perfect for forward propagation operation, which happen in inference. Finally, as we expect, inference time on cluster with C5 and T2 instances, which do not have any GPU, are much slower than the others. As I said, increasing number of nodes reduce inference time linearly. But if we want to see increasing number of nodes, how can impact cost of inference, we need to plot price of inference for each video for different number of child nodes. In this figure, we plotted this criteria. As you can see, for G4DN and P3 cluster, for different number of nodes, almost the final price for each video is constant. It means by increasing number of nodes, although we need to pay for more nodes, the time which this increment buy for us compensate that overpay. On the other hand, as you can see, although C5 and T2 increase instances are cheaper instances, since they need lots of computation time, at the end of the day, they would be more expensive for us. As you can see, G4DN is cheapest, and also we saw it is the fastest cluster type, and I can easily say it would be our best candidate. In this diagram, with a better magnitude, you can see how drastically increasing number of nodes reduce inference time. With having all these numbers in mind, and considering the fact which we have more than 1 million videos in our dataset, on a cluster of G4DN with 50 child nodes, it took about more than 8 days to reduce all data. Okay, let's start talking about the second case study, which is runway detection. Runway driving is one of the most dangerous events in the transportation, which usually results in fatal incidents. Detection of these events in real-time basis can help driver to avoid any accident by triggering several alarms for the driver. Although there are several solutions for this problem. Here, we focused on a computer vision-based solution which uses CCTV cameras which are already located in highways. In this solution, a stream of the camera would be input of the deepest stream to detect and track all vehicles passing in front of the camera. Using this data, we can calculate velocity of each vehicle, and by training a model, which is a combination of Gaussian mixture model and SVM classification model, we will learn what is the permitted velocity at each section of the road. Finally, by comparing velocity of new coming vehicles with this permitted velocity, we decide if the driver is driving on the wrong side or right side. Let's see how we can scale this solution up. We used 8 virtual CPU with 30 gigabytes in addition. And also we used 2 NVIDIA T4 GPUs for video analysis and a 3 terabyte persistent disk for data storage. The perception module can take multiple video streams as input. So it requires developer to twiddle the number of video streams that they need to simultaneously process in each single GPU to achieve a balance between performance and cost. We used built-in NVIDIA deep-stream functionality to determine the processing latency of 3 main components with various number of traffic cameras. Results of this latency analysis are presented here in this figure. As you can see, in order to have a near real-time performance, we should distribute 80 cameras to each T4 GPU so that the overall processing latency caused by the perception module remains less than 1 second. To measure the operating cost in detail, we implemented the proposed framework using the GCP for 5 days. The GCP provides a sustained use discount cost based on monthly usage level. And in this figure, we show the average daily cost with and without the sustained use discount. Okay, finally, let's see what's the ongoing research in distributed learning in transportation and how it can help us to train better models. Alzheimer's, mental disabilities, and other cognition disabilities are sets of diseases which can impact driving ability of the patient hazardously. The goal of this project is to detect signs of these diseases in driving behavior of the driver. For this manner, in addition to the very rich naturalistic driving data that we have, we also need to have a complete data over medical status of each driver. This data include results of MOCA test, MMSE test, which both are clinical tests for detection of Alzheimer's, and it could be age. With this data, we can generate a cognition stat score and observe driving behavior of each driver using in-the-cabin camera and outside-faced camera. Also, to make detection of anomaly easier in our dataset, we only consider those driving on the ramps coming from or merging into a highway. A structure of the model which we have used in this project is depicted here. We are subtracting each image of the video from the next image and use a pre-trained ResNet model to analyze these visual data. Then, by using a convolutional LSTM, we track change of these features in time and finally decide over cognition situation of the driver. Okay, in this slide, we show the structure of training our model on a cluster of child nodes. In this structure, we are using federated averaging algorithm to train our model. As you can see, data will be distributed over different child nodes, and on each node, the model will be trained separately. Then the suggested gradient of weight will be shared with the master node, and it gathered this amount from all different nodes, and by getting an average of these gradients, it determines a unique gradient and return it to all nodes for the next epoch. By continuing and iteratively doing this process, we can train a model with high accuracy. Finally, if you are interested in any of these projects and want to read more about them, here you can find more details of them in these references. Thank you, and I'm glad to answer any questions.